Hi, I'm Dr. Paul Mason, and today I'm going to speak about Kepler and Kepler's laws of planetary motion. This is set in context with Kepler's um, involvement with Tycho Brahe in Prague about the year 1601, that at that time Kepler worked as Tycho's assistant. Tycho's data was held very close to him, and he didn't really allow Kepler the ability to look at his data too closely. Kepler was a very strong mathematician, and he was able to, once as he gained access to data, was able to analyze it in different ways than Tycho had done. And first of all, during those years, he tried to see if Tycho's model was correct, and the Copernican model, and found that if he applied a little bit of a change where he tried a sort of an egg shape as opposed to a circle, then he could sort of get a closer fit to the observations of Mars. Especially Mars was the object being analyzed in most detail because the data was so good in terms of vast numbers of data points on Mars that Tycho had available. And so eventually, though, after about 40 tries and several years, ultimately he came upon the solution, which was an ellipse. And so the first law of Kepler is that we call it the Kepler's laws of planetary motion. Planets orbit around the sun along ellipses with the sun at one focus. And so we have a planet orbiting here, and this is not an oval or egg shape. It's a very particular geometrical shape. You can get that exact shape by taking a cone and slicing it. If you slice it exactly horizontal, you get the shape of a circle. If you cut it at very sharp angles like this, you can get a parabola or a hyperbola. But if you cut it at just a slight angle like that, you can get an ellipse. You also have a feature that an ellipse has every point on the ellipse. If you add the distance from the sun to that point to the other focus, that's the same for every point along the ellipse. And so Kepler finally saw that this was the solution. It didn't exactly come all at once as I described, and I'll talk about that in a moment. But first, I just want to emphasize that this was done by enormous amounts of data that was provided by Tycho Brahe. After Tycho's death, Kepler had full access to the data and had about 40 tries of different kinds of non-circular shapes before figuring out that the ellipse was the proper result of that. And so the second law that he found along the way was that planets sweep out equal areas in equal amounts of time. And so the way that you can look at this is a simple picture here that is graphically correct, that we have the orbit course, the sun is much smaller. This is not to scale. But the planet orbiting around, say, goes this way. One thing that we know is that the actual orbits of planets are quite circular, but they can be more elliptical and have a higher eccentricity. But it's easier to see with a planet with a higher eccentricity to see the effect of Kepler's laws here. So the second law is that if you start at a particular time here and then wait a particular time, like a month, that planet will sweep out an area equal here that we call A. And if you wait till another time, let's call this a month. If this was a month, then the planet would travel from here to here, sweep out this area. This area is exactly the same as this area, which means that the planet had to slow down a little bit compared to here. Out here, also a month, the planet would travel slower because there is such a long path, long distance between the sun and the planet, and so it sweeps out an area that's equal in all three cases. So the way the law is stated is that planets sweep out equal amounts of area in equal amounts of time. The consequence of that is that planets speed up when close to the sun and slow down when far away from the sun. And so as Kepler was working on the problem, he saw that this was a property that the planets had in their orbits. We can see it in action here. The planet is orbiting around and it moves slower. The perihelion is where the planet is closest to the sun, which is right there. The aphelion is right there, the point in which the planet is most distant from the sun. And again, this is true for all ellipses, and planets have much more circular orbits, and the actual objects here are exaggerated dramatically in size. However, the motion and the velocity is correct. So, Kepler's third law is actually the first thing that he came up with as he worked and tried to figure this out. What he thought about was that there probably was a mathematical relationship in how the different planets moved around the sun with respect to each other. And so he realized that the planets that were further away from the sun were moving slower. The planets that were closer to the sun were moving faster. And so he thought about a relationship between the period, which is P here, and all in comparison with the Earth, where P is measured in years. So for Earth, that would be 1. And A, which is the semi-major axis of the ellipse, or actually the average distance between the planet and the sun, measured in astronomical units, meaning that it's also 1 for the Earth. So he worked with different ideas and came up with this harmonic law, which is that if you square the period and divide it by the average distance between the planet and the sun cubed, you would get 1, meaning that all of the planets fall along this line here between the period on the horizontal axis and the semi-major axis, which is the same as the average distance from the planet to the sun, plotted here, and you see that not only do they all follow on the same line, but this line has a slope of 1 because you're measuring this in the special units where the A is in astronomical units. An astronomical unit is by definition the distance between the Earth and the sun, the average distance between the Earth and the sun. So this has to be 1 for the Earth, and but it also is 1 for all of the planets. And ultimately, Isaac Newton came along after Kepler and found that gravity, or described that the idea that gravity was the cause of this harmonic law, because this constant over here was equal to 2 pi over g, the constant, universal constant of gravitation, times the sum of the masses, one mass being the sun, the second mass being the planet orbiting the sun in that case. And so this is called Newton's version of Kepler's third law.